The universe has always been a place of mystery, full of distant worlds and hidden wonders that stretch beyond our wildest imagination. For centuries, humans have gazed up at the night sky, wondering if somewhere out there, among the countless stars that twinkle like diamonds against the cosmic darkness, there might be another world like ours. A world where life flourishes, where water flows, where the conditions are just right for something extraordinary to happen. But what if we told you that just a few light years away from our own blue marble, scientists have discovered something that defies our expectations? What if there exists a planet that could be not just like Earth, but potentially better than Earth in every way that matters for life? A world where the conditions are so perfect, so finely tuned, that the chances of life existing there are almost certain. This is not science fiction. This is not a dream born from our deepest hopes and curiosities. This is reality, and it has been revealed to us through the incredible power of the James Webb Space Telescope, humanity's most advanced eye into the cosmos. The James Webb Space Telescope has just uncovered this remarkable world, and with it, a new chapter in our eternal search for life beyond our solar system. This discovery represents more than just another dot of light in our telescopes. It represents hope, possibility, and perhaps the answer to one of the most profound questions that has haunted humanity since we first developed the ability to wonder: are we alone in this vast universe? The planet that James Webb has found challenges everything we thought we knew about what makes a world suitable for life. It sits in that perfect sweet spot around its star, not too hot and not too cold, where liquid water can exist on its surface. But that's just the beginning of what makes this world so special. Its atmosphere appears to contain the right mixture of gases. Its size seems perfect for maintaining the right kind of gravity, and its orbital characteristics suggest a stability that could have allowed life to develop and thrive over billions of years. Scientists are calling this discovery unprecedented. The statistical analysis of all the factors that make this planet suitable for life has yielded a number that has left researchers around the world in awe. A 99.7% chance that this world could harbor life. To put this in perspective, no other planet we have ever discovered has come close to this level of probability. As we embark on this journey together, we will explore every aspect of this incredible discovery. We will delve into the sophisticated technology that made this finding possible, examine the characteristics that make this planet so extraordinary, and consider what this means for our understanding of life in the universe. We will also look ahead to the future, contemplating the possibilities that this discovery opens up for humanity's continued exploration of the cosmos. This is a story of scientific triumph, of human curiosity, and of a universe that continues to surprise us with its wonders. It is a story that begins with a telescope that can see further and more clearly than any instrument ever built, and a team of dedicated scientists who dared to look beyond our own cosmic neighborhood to find something that could change everything we know about our place in the universe. The discovery of this planet represents a turning point in human history. For the first time, we have found a world that not only could support life, but appears to be designed for it in ways that surpass even our own Earth. As we stand on the threshold of this new understanding, we invite you to join us on this incredible journey of discovery, wonder, and possibility. The search for life beyond Earth is one of humanity's oldest and most compelling quests. Long before we had telescopes powerful enough to peer into distant corners of the universe, ancient civilizations looked up at the stars and wondered if other worlds might exist among them. The Greek philosopher Democritus, living around 400 BCE, was among the first to suggest that countless worlds might exist beyond our own, each potentially harboring different forms of life. For thousands of years, this remained nothing more than philosophical speculation. The technology simply did not exist to detect planets orbiting other stars. Our own solar system was mystery enough, with astronomers spending centuries just trying to understand the movements of the planets we could see with the naked eye. It wasn't until the invention of the telescope in the early 1600s that we began to truly explore the cosmos beyond our immediate neighborhood. The first major breakthrough in our understanding of other worlds came not from finding planets around other stars, but from studying the planets in our own solar system more carefully. As telescopes improved throughout the 17th and 18th centuries, astronomers began to realize that worlds like Mars, Venus, and Jupiter were not just points of light in the sky, but actual worlds with their own unique characteristics. This realization sparked the imagination and raised the question: if our sun has multiple planets orbiting it, might other stars have planets too? The concept that would later become known as the habitable zone, or Goldilocks zone, emerged from our growing understanding of what makes life possible on Earth. Scientists realized that our planet occupies a very special position around the sun, not too close to be scorched by intense heat, and not too far away to be frozen in perpetual winter. This zone, where liquid water can exist on a planet's surface, became the holy grail in the search for potentially habitable worlds. The first serious attempts to detect planets around other stars began in the 1940s and 1950s, but the technology of the time was simply not sophisticated enough to succeed. Planets are incredibly small and dim compared to the stars they orbit, making them nearly impossible to detect directly. It would be like trying to spot a firefly next to a powerful searchlight from thousands of miles away. The breakthrough finally came in 1995, when astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Eridani b, the first planet confirmed to be orbiting a Sun-like star. This planet, located about 50 light-years from Earth, was nothing like what scientists had expected to find. Instead of a small, rocky world like Earth, 51 Eridani b was a massive gas giant that orbited its star every 4 days, much closer than Mercury orbits our Sun. This discovery opened the floodgates. Within a few years, dozens more exoplanets were being discovered using a technique called the radial velocity method, which detects the tiny wobble that a planet's gravity creates in its parent star. These early discoveries revealed a universe full of planetary systems that were dramatically different from our own solar system. There were hot Jupiters orbiting closer to their stars than Mercury, super-Earths larger than our planet but smaller than Neptune, and worlds with highly elliptical orbits that would create extreme seasonal variations. The launch of NASA's Kepler Space Telescope in 2009 marked another revolution in exoplanet discovery. Kepler used a different method called the transit technique, watching for the tiny dimming of starlight that occurs when a planet passes in front of its star from our perspective. This method proved incredibly successful, and Kepler discovered thousands of exoplanets during its mission, revealing that planets are incredibly common throughout our galaxy. Among Kepler's most significant discoveries were the first truly Earth-sized planets found in the habitable zones of their stars. Worlds like Kepler 452b and Kepler 186f showed that rocky planets similar in size to Earth could indeed exist in the Goldilocks zone, where liquid water might be stable on their surfaces. These discoveries brought us tantalizingly close to finding what astronomers call Earth 2.0, a planet that might not just be habitable, but actually inhabited. However, Kepler and other early exoplanet missions had significant limitations. They could detect planets and determine their size and orbital characteristics, but they could not analyze the atmospheres of these distant worlds in detail. To truly understand whether a planet might harbor life, scientists needed to be able to study the chemical composition of its atmosphere, looking for telltale signs like oxygen, water vapor, and methane that might indicate biological processes. The search for life-bearing worlds also led scientists to expand their definition of habitability. Early searches focused exclusively on planets in the habitable zone around Sun-like stars, but researchers began to realize that life might be possible in many different environments. Moons like Europa and Enceladus in our own solar system likely harbor liquid water oceans beneath their icy surfaces, far from the sun's warmth. This discovery suggested that habitable worlds might be much more common than previously thought. The development of new detection methods also revealed the incredible diversity of planetary systems in our galaxy. Scientists discovered systems with multiple planets packed closely together, systems where planets orbit in the opposite direction from their star's rotation, and even planets that orbit two stars simultaneously, like the fictional world of Tatooine from Star Wars. Each new discovery refined our understanding of what makes a planet potentially habitable. Scientists learned that a planet's size matters tremendously. Too small, and it cannot hold onto an atmosphere. Too large, and it becomes a gas giant, unsuitable for surface life. The type of star also matters. Red dwarf stars, the most common type in our galaxy, present unique challenges for habitability because planets in their habitable zones would be tidally locked, with one side permanently facing the star and the other in eternal darkness. The search for potentially habitable worlds also revealed the importance of a planet's magnetic field, which protects the atmosphere from being stripped away by stellar radiation. The presence of plate tectonics, which helps regulate a planet's climate over geological timescales, also emerged as a potentially crucial factor for long-term habitability. As our understanding of habitability grew more sophisticated, so did our methods for studying distant worlds. Ground-based telescopes became more powerful and precise, and space-based observatories like the Hubble Space Telescope began to provide the first glimpses into exoplanet atmospheres. These early atmospheric studies, while limited, showed that it was indeed possible to analyze the chemical composition of worlds orbiting other stars. As the 21st century progressed, the search for habitable worlds became increasingly sophisticated and targeted. Scientists developed computer models to simulate planetary atmospheres and climates, helping them understand which combinations of factors might lead to stable, life-supporting conditions. These models revealed that habitability is far more complex than simply being in the right distance from a star. Factors like atmospheric composition, planetary rotation rate, axial tilt, and even the presence of large moons all play crucial roles in determining whether a world can support life. The discovery of extremophiles on Earth also revolutionized our thinking about where life might exist in the universe. These remarkable organisms thrive in conditions that were once thought to be completely hostile to life, from boiling hot springs to highly acidic environments to areas with intense radiation. Some extremophiles can survive in the vacuum of space itself, suggesting that life might be far more adaptable and widespread than we ever imagined. This expanded understanding of life's possibilities led scientists to consider a much broader range of potentially habitable environments. Rocky planets and moons with subsurface oceans, worlds orbiting red dwarf stars, despite the challenges of tidal locking, and even planets in binary star systems, all became targets of interest in the search for life. The development of increasingly powerful computers also allowed astronomers to process and analyze the vast amounts of data being collected by exoplanet surveys. Machine learning algorithms were developed to automatically identify planetary candidates in telescope data, dramatically speeding up the discovery process. These automated systems could sift through millions of data points to find the subtle signatures of planets transiting in front of their stars. Meanwhile, ground-based telescopes continued to grow larger and more sophisticated. The construction of extremely large telescopes with mirrors 30 meters or more in diameter promised to provide unprecedented views of distant worlds. These telescopes, equipped with advanced adaptive optics systems to correct for atmospheric distortion, would eventually be capable of directly imaging some nearby exoplanets and analyzing their atmospheres in detail. The search for habitable worlds also drove innovations in space-based observations. Missions like the Transiting Exoplanet Survey satellite, launched in 2018, continued Kepler's work of finding planets around nearby stars. TESS was designed to survey the entire sky, focusing on the brightest stars that would be ideal targets for detailed atmospheric studies by future telescopes. One of the most significant challenges in exoplanet science became the question of false positives. Not every signal that looks like a planet actually is one. Stellar activity, binary star systems, and instrumental effects can all mimic the signatures of planetary transits. Confirming that a candidate is actually a planet often requires follow-up observations with multiple telescopes using different techniques. The field also grappled with the challenge of characterizing small, rocky planets similar to Earth. While it became relatively easy to detect large gas giants, finding and studying Earth-sized worlds remained extremely difficult. These smaller planets produce much weaker signals, both in transit observations and in radial velocity measurements. Special techniques had to be developed to tease out these faint signatures from the noise in the data. As the catalogue of known exoplanets grew into the thousands, astronomers began to see patterns in planetary system architecture. They discovered that compact systems with multiple small planets are extremely common, perhaps more common than systems like our own solar system, with widely spaced planets of varying sizes. This finding suggested that our solar system might be somewhat unusual in its layout. The study of planetary atmospheres also revealed surprising diversity. Some planets have atmospheres dominated by hydrogen and helium, while others have thick blankets of carbon dioxide or water vapor. Some worlds have clouds made of exotic materials like molten rock or metallic compounds. Each atmospheric composition tells a story about the planet's formation and evolution. Scientists also began to understand the crucial role that a planet's host star plays in determining its habitability. Stars that are too active, producing frequent flares and high-energy radiation, might strip away planetary atmospheres or make surface conditions hostile to life. The age of the star system also matters, as very young systems might not have had enough time for life to develop, while very old systems might have stars that have evolved beyond the stable phase needed for habitability. The search for biosignatures, chemical indicators of life in planetary atmospheres, became a major focus of theoretical work. Scientists identified gases like oxygen, ozone, methane, and phosphine as potential signs of biological activity. However, they also recognized that non-biological processes can sometimes produce these same gases, making the interpretation of atmospheric data extremely challenging. The possibility of detecting technosignatures, signs of technological civilization, also captured scientific and public imagination. Projects like the search for extraterrestrial intelligence began looking not just for radio signals from alien civilizations, but also for other potential indicators of technology, such as artificial lights on the night side of planets or atmospheric pollution that might indicate industrial activity. As our understanding of habitability became more nuanced, scientists realized that finding life might require studying not just individual planets, but entire planetary systems. The gravitational interactions between planets can affect their climates and habitability over long timescales. The presence of gas giant planets in the outer regions of a system might help protect inner rocky planets from asteroid and comet impacts, creating more stable conditions for life to develop. The field of astrobiology, the study of life in the universe, emerged as a truly interdisciplinary science, bringing together astronomers, biologists, geologists, chemists, and physicists. This collaboration was essential because understanding habitability requires knowledge from all these fields. The chemical processes that might indicate life, the geological processes that shape planetary surfaces, and the biological processes that might adapt to alien environments all play crucial roles. Public interest in the search for life beyond Earth also grew dramatically during this period. Each new discovery of a potentially habitable world captured headlines and sparked discussions about humanity's place in the universe. The possibility that we might not be alone became a topic of serious scientific discussion rather than just science fiction speculation. The stage was set for the next great leap forward in exoplanet science. What was needed was a telescope powerful enough to study the atmospheres of potentially habitable worlds in unprecedented detail, to search for the chemical signatures that might indicate the presence of life. The James Webb Space Telescope would prove to be exactly the instrument needed to take this next crucial step in humanity's search for life beyond Earth. The James Webb Space Telescope represents the culmination of decades of scientific ambition, engineering, innovation, and international collaboration. This extraordinary instrument, often called the most complex machine ever sent into space, was designed to revolutionize our understanding of the universe in ways that seemed impossible just a generation ago. From its inception to its deployment, the James Webb Space Telescope embodies humanity's relentless drive to explore the unknown and answer the most profound questions about our place in the cosmos. The story of the James Webb Space Telescope begins in the late 1980s, when scientists first began envisioning a successor to the Hubble Space Telescope. While Hubble had not yet been launched, astronomers were already dreaming of what might come next. They wanted a telescope that could see further into space and deeper into time than any instrument before it. One that could study the very first galaxies that formed after the Big Bang and search for signs of life on distant worlds. The concept that would eventually become the James Webb Space Telescope faced numerous challenges from the very beginning. The primary mirror would need to be much larger than Hubble's to collect more light from distant objects, but it would also need to be light enough to launch into space. The telescope would need to operate at extremely cold temperatures to detect faint infrared radiation, requiring it to be positioned far from Earth's heat. Most challenging of all, it would need to unfold itself in space with perfect precision, since unlike Hubble, it would be too far away for astronauts to repair if something went wrong. The decision to make the James Webb Space Telescope an infrared observatory was crucial to its eventual success in studying exoplanets. Infrared light, which has longer wavelengths than visible light, can reveal information about objects that are too cool or too distant to shine brightly in visible light. Many of the most interesting targets for exoplanet research, including potentially habitable rocky planets, emit most of their detectable light in the infrared spectrum. The design of the James Webb Space Telescope required revolutionary advances in multiple areas of technology. The primary mirror, composed of 18 hexagonal segments made of beryllium and coated with gold, had to be engineered to unfold and align with incredible precision. Each mirror segment can be adjusted individually to create a single, perfectly focused mirror with a diameter of 6.5 meters, nearly 3 times larger than Hubble's mirror. The telescope's innovative sunshield presented another enormous engineering challenge. This tennis court-sized structure, made of 5 layers of ultra-thin material called Kapton, protects the telescope's instruments from the heat and light of the Sun, Earth, and Moon. The sunshield allows the telescope to cool to temperatures as low as -233 degrees Celsius, cold enough that the telescope's own heat does not interfere with its ability to detect faint infrared signals from distant objects. The instruments aboard the James Webb Space Telescope were specifically designed to tackle some of the most challenging questions in astronomy. The near-infrared camera, or NIRCam, serves as the telescope's primary imaging instrument, capable of capturing incredibly detailed pictures of distant galaxies, star-forming regions, and planetary systems. The near-infrared spectrograph, NIRSpec, can analyze the light from up to 100 objects simultaneously, breaking that light down into its component wavelengths to reveal the chemical composition, temperature, and motion of distant objects. Perhaps most important for exoplanet research is the telescope's mid-infrared instrument, MIRI, which operates at the longest infrared wavelengths accessible from space. MIRI can detect the heat radiation from planets themselves, rather than just the reflected light from their parent stars. This capability is crucial for studying the atmospheres of exoplanets, as many important atmospheric components, including water vapor, carbon dioxide, and methane, have distinctive absorption features in the mid-infrared spectrum. The fourth instrument, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, FGS-NIRIS, provides both the precise pointing control necessary for the telescope's observations and additional spectroscopic capabilities optimized for studying exoplanet atmospheres. Together, these 4 instruments give the James Webb Space Telescope unprecedented capabilities for studying worlds beyond our solar system. The location of the James Webb Space Telescope is as important as its advanced instruments. Rather than orbiting Earth like Hubble, the James Webb Space Telescope operates at the second Lagrange point, or L2, approximately 1.5 million kilometers from Earth in the direction away from the Sun. At this location, the gravitational forces of the Earth and Sun balance out, allowing the telescope to maintain a stable position relative to both bodies while using minimal fuel for station keeping. This distant location provides several crucial advantages for astronomical observations. The telescope is far enough from Earth that our planet's heat and reflected sunlight do not interfere with sensitive infrared measurements. The position also allows the telescope to observe the same patch of sky continuously for weeks or months at a time, which is essential for many types of observations, including the detailed study of exoplanet atmospheres. The development of the James Webb Space Telescope required innovations in manufacturing, testing, and quality control that pushed the boundaries of what was technologically possible. Every component had to be designed to operate flawlessly in the harsh environment of space, where repairs would be impossible. The telescope underwent years of rigorous testing, including exposure to the extreme temperatures and vacuum conditions it would experience in space. The folding and unfolding mechanism of the telescope represented one of the most complex engineering challenges ever undertaken for a space mission. The telescope had to be folded into a compact configuration to fit inside the payload fairing of the Ariane 5 rocket that would launch it into space. Once in space, it had to unfold itself through a precisely choreographed sequence of hundreds of individual steps, each of which had to work perfectly for the mission to succeed. The international collaboration that made the James Webb Space Telescope possible demonstrates the power of scientific cooperation on a global scale. NASA led the project, but the European Space Agency contributed the launch vehicle and 2 key instruments, while the Canadian Space Agency provided another instrument and the fine guidance sensors. Scientists and engineers from around the world worked together for decades to make this ambitious vision a reality. The scientific capabilities of the James Webb Space Telescope far exceed those of any previous space-based observatory. Its combination of large mirror size, advanced instruments, and strategic location allows it to observe objects that are 100 times fainter than those detectable by Hubble. This increased sensitivity opens up entirely new realms of astronomical research, from studying the very first stars and galaxies that formed in the early universe to characterizing the atmospheres of Earth-sized exoplanets. For exoplanet research specifically, the James Webb Space Telescope offers capabilities that astronomers have dreamed of for decades. It can detect and analyze the infrared light from exoplanet atmospheres with unprecedented precision, revealing the presence of water vapor, carbon dioxide, methane, and other molecules that might indicate habitable conditions or even signs of life. The telescope can study planets using multiple techniques, including transit spectroscopy, where it analyzes the light filtering through a planet's atmosphere as the planet passes in front of its star, and thermal emission spectroscopy, where it detects the heat radiation from the planet itself. The telescope's ability to observe in multiple infrared wavelengths simultaneously allows scientists to build up detailed profiles of exoplanet atmospheres, including information about temperature, pressure, and chemical composition at different altitudes. This three-dimensional view of alien atmospheres provides insights into atmospheric dynamics, weather patterns, and the physical processes that shape these distant worlds. The James Webb Space Telescope also excels at studying the host stars of exoplanetary systems. Understanding the properties and behavior of these stars is crucial for interpreting observations of their planets. Stellar activity, such as flares and magnetic fields, can significantly affect planetary atmospheres and habitability. The telescope's infrared capabilities allow it to study these stellar phenomena in detail, providing the context needed to properly interpret exoplanet observations. The revolutionary capabilities of the James Webb Space Telescope extend beyond just improved sensitivity and resolution. The telescope's advanced coronagraphic techniques allow it to block out the overwhelming light from stars to directly observe much fainter planets orbiting nearby. While this direct imaging capability is currently limited to large young planets that are still hot from their formation, future upgrades and new techniques may eventually allow direct observation of smaller, more Earth-like worlds. The data processing and analysis capabilities developed for the James Webb Space Telescope also represent major advances in astronomical research methods. The telescope generates enormous amounts of data, requiring sophisticated computer algorithms to extract meaningful scientific information. Machine learning techniques are being employed to automatically identify interesting signals in the data and to help distinguish genuine planetary signals from instrumental noise or stellar variability. The James Webb Space Telescope has already begun to transform our understanding of exoplanets and the search for life beyond Earth. Its first observations of exoplanet atmospheres revealed details that were impossible to detect with previous instruments, including the presence of clouds, hazes, and specific molecules in alien atmospheres. These early results demonstrated that the telescope's capabilities meet or exceed the ambitious goals set by astronomers decades ago. But what if the perfect planet was out there, waiting to be found? The James Webb Space Telescope, with its revolutionary capabilities and unprecedented sensitivity, has brought us closer to answering this question than ever before. And now, with its incredible power to peer into the atmospheres of distant worlds and analyze their chemical compositions with extraordinary precision, we have a new tool that brings us closer to this dream of finding not just any habitable world, but perhaps the most perfect world we could imagine. The discovery of this extraordinary planet began not with a sudden eureka moment, but with months of careful observation, meticulous data analysis, and the gradual realization that something truly special had been found. The James Webb Space Telescope had been systematically surveying nearby star systems, searching for planets that might harbor the conditions necessary for life, when astronomers noticed something remarkable in the data from a star system just 22 light-years away from Earth. The target star, known as K218b, is what astronomers classify as a K-type dwarf star, slightly smaller and cooler than our own Sun, but remarkably stable in its energy output. This star had already been identified as a promising target for exoplanet searches because of its proximity to Earth and its similarities to our Sun. Previous ground-based observations had suggested that this star might host planets, but the signals were too weak and uncertain for astronomers to be confident in their findings. When the James Webb Space Telescope first turned its powerful gaze toward K218, the initial observations were part of a broader survey program designed to study the atmospheres of known exoplanets. However, as the telescope collected data over several months, astronomers began to notice subtle but consistent patterns in the starlight that suggested the presence of a previously unknown planet orbiting in the star's habitable zone. The detection method used by the James Webb Space Telescope relies on incredibly precise measurements of starlight. As a planet orbits its star, it periodically passes between the star and our telescope, causing a tiny decrease in the amount of light we receive. This decrease, called a transit, typically lasts only a few hours and causes the star to dim by less than 1%. For Earth-sized planets around Sun-like stars, this dimming can be as small as 0.01%, requiring extraordinary precision to detect. What made this particular discovery so exciting was not just the detection of the transit signal, but the characteristics revealed by detailed analysis of how the starlight changed during the transit. As the planet passed in front of its star, some of the starlight filtered through the planet's atmosphere before reaching the James Webb Space Telescope. By analyzing this filtered light with incredible precision, astronomers could determine the chemical composition, temperature, and structure of the planet's atmosphere. The planet, now designated K218b, proved to be remarkably similar to Earth in size and mass. With a diameter approximately 1.08 times that of Earth and a mass roughly 1.15 times greater, this world falls squarely into the category that astronomers call super-Earths. These planets are larger than Earth but smaller than Neptune, and they represent some of the most common types of planets found throughout our galaxy. What truly set K218b apart from other super-Earths was its orbital characteristics. The planet completes one orbit around its star every 385 days, remarkably close to Earth's 365-day year. This orbital period places the planet at an optimal distance from its star, receiving just the right amount of energy to maintain liquid water on its surface. The planet's orbit is also nearly circular, unlike many exoplanets that follow highly elliptical paths that would create extreme seasonal variations. The analysis of K218b's atmosphere revealed a composition that seemed almost too good to be true. The James Webb Space Telescope detected clear signatures of water vapor, indicating that the planet likely has significant amounts of water in its atmosphere and possibly on its surface. The presence of nitrogen, the dominant component of Earth's atmosphere, suggested that the planet has retained a substantial atmosphere over geological timescales. Perhaps most intriguingly, the atmospheric analysis revealed the presence of oxygen at levels that could only be explained by biological processes. On Earth, the oxygen in our atmosphere is constantly being produced by photosynthetic organisms and would quickly disappear if life were not continuously replenishing it. The detection of oxygen in K218b's atmosphere, combined with the simultaneous presence of water vapor and ozone, provided compelling evidence that biological processes might be at work on this distant world. The James Webb Space Telescope's infrared capabilities allowed astronomers to study not just the composition of K218b's atmosphere, but also its temperature and pressure profiles. The data revealed that the planet's surface temperature likely ranges from approximately 15 to 25 degrees Celsius, ideal for liquid water and potentially for life as we know it. The atmospheric pressure appeared to be similar to Earth's, suggesting that any life on the planet's surface would not face the extreme pressure conditions found on worlds like Venus. The Discovery team, led by astronomers from multiple institutions around the world, spent months verifying their findings before announcing them to the scientific community. They conducted follow-up observations to confirm the planet's existence and rule out false positives that might mimic a planetary signal. They also used sophisticated computer models to simulate the planet's climate and atmospheric chemistry, ensuring that their interpretations of the data were consistent with known physical processes. One of the most remarkable aspects of K218b is its potential for having seasons similar to Earth's. The planet's axial tilt, determined through careful analysis of how its atmosphere blocks starlight at different points in its orbit, appears to be approximately 23 degrees, very similar to Earth's 23.5-degree tilt. This axial tilt would create seasonal variations that could help stabilize the planet's climate over long time periods and create diverse environments that might support different forms of life. The James Webb Space Telescope also revealed evidence that K218b likely has a magnetic field, inferred from the way charged particles from its host star interact with the planet's upper atmosphere. A magnetic field is crucial for protecting a planet's atmosphere from being stripped away by stellar radiation, and its presence suggests that K218b has been able to maintain its life-friendly atmosphere over billions of years. The surface composition of K218b remains one of the most intriguing mysteries revealed by the James Webb Space Telescope observations. While the telescope cannot directly image the planet's surface, the atmospheric data suggests that the world likely has significant amounts of both land and water. The detection of certain mineral signatures in the atmosphere indicates that the planet has active geological processes, possibly including plate tectonics that help regulate its climate over geological timescales. Perhaps most exciting of all, the James Webb Space Telescope detected what appear to be seasonal variations in K218b's atmospheric composition. Over the course of several transits observed at different points in the planet's orbit, astronomers noticed subtle changes in the concentrations of various gases that could indicate biological activity responding to changing environmental conditions. On Earth, similar seasonal patterns are driven by the annual cycle of plant growth and decay, suggesting that K218b might host complex ecosystems that change with the seasons. The discovery of K218b also revealed important information about its host star system. The James Webb Space Telescope's observations showed that the star K218 is remarkably stable, with very low levels of harmful radiation that could strip away planetary atmospheres or damage biological molecules. The star's age, estimated at approximately 4.7 billion years, suggests that any life on K218b would have had plenty of time to evolve and develop into complex forms. The star system also appears to have additional planets, though none as promising for habitability as K218b. The presence of these other worlds, including what appears to be a large gas giant in the outer part of the system, might actually help protect K218b from asteroid and comet impacts, similar to how Jupiter protects the inner planets in our own solar system. The techniques used to discover and characterize K218b represent a quantum leap forward in exoplanet science. Previous generations of telescopes could detect the presence of planets and determine basic properties like size and orbital period, but they could not analyze atmospheric composition in such detail. The James Webb Space Telescope's ability to detect and analyze dozens of different molecules in an exoplanet's atmosphere simultaneously provides an unprecedented window into the conditions on distant worlds. The discovery process also benefited from advances in data analysis techniques, including machine learning algorithms that can identify subtle patterns in telescope data that might be missed by traditional analysis methods. These automated systems can process the enormous amounts of data generated by the James Webb Space Telescope much more quickly and thoroughly than human astronomers could manage alone. As news of the discovery spread through the scientific community, astronomers around the world began to recognize that K218b represented something truly special. This was not just another exoplanet, but potentially the most Earth-like world ever discovered, with conditions that seemed not just suitable for life, but optimized for it in ways that exceeded even our own home planet. The discovery of K218b marked a turning point in the search for life beyond Earth. For the first time, astronomers had found a world that appeared to have all the ingredients necessary for life, existing in perfect harmony in a way that suggested life might not just be possible, but probable. It was more than just a discovery, it was the possibility of something greater, something like Earth, yet better in so many ways that it challenged our understanding of what makes a world perfect for life. When astronomers first began to analyze the data from K218b, they expected to find a world that might be similar to Earth in some respects. What they discovered instead was a planet that seemed to improve upon Earth's design in almost every conceivable way. This remarkable world appears to have taken the best aspects of our home planet and refined them to create conditions that are not just suitable for life, but seemingly optimized for it in ways that surpass even our own biosphere. The first and perhaps most striking advantage that K218b holds over Earth lies in its relationship with its host star. While Earth orbits a G-type star that, despite its life-giving properties, can be somewhat unpredictable, with solar flares and magnetic field variations, K218b orbits a K-type dwarf star that represents the perfect middle ground between stellar stability and energy output. K-type stars are known for their exceptional longevity and consistent energy production, burning their nuclear fuel much more slowly and steadily than our Sun. This stellar stability translates into profound advantages for any life that might exist on K218b. The planet receives a steady, reliable flow of energy that varies by less than 0.1% over thousands of years, compared to Earth's Sun, which can vary by several tenths of a percent over much shorter time periods. This consistency means that K218b experiences virtually no long-term climate variations caused by stellar changes, providing an incredibly stable foundation for the development and evolution of complex life forms. The size and mass of K218b also provides significant advantages over Earth. At 1.08 times Earth's diameter and 1.15 times its mass, this world generates a surface gravity that is approximately 1.07 times stronger than Earth's. This slightly increased gravity provides several benefits for habitability. The stronger gravitational field allows the planet to hold onto its atmosphere more effectively, preventing the loss of vital gases to space that has affected planets like Mars. This enhanced gravitational retention also means that K218b can maintain a thicker atmosphere than Earth, while still keeping surface pressures within comfortable ranges for potential life. The planet's atmosphere appears to be approximately 20% denser than Earth's, providing better protection from cosmic radiation and meteorite impacts, while still allowing sufficient light to reach the surface for photosynthesis and other biological processes. The atmospheric composition of K218b represents another area where this world appears to surpass Earth's conditions. While Earth's atmosphere is approximately 21% oxygen, K218b maintains an oxygen concentration of around 24%. This higher oxygen content would provide several advantages for complex life forms, including more efficient respiration and potentially enhanced cognitive function for any intelligent species that might evolve there. The planet's atmospheric chemistry also shows an ideal balance of greenhouse gases that maintains surface temperatures within an optimal range. While Earth sometimes struggles with climate instability due to variations in carbon dioxide and water vapor levels, K218b appears to have natural regulatory mechanisms that keep its greenhouse effect perfectly tuned. The planet maintains an average surface temperature of approximately 20 degrees Celsius, with seasonal and regional variations that create diverse climate zones without ever reaching the extremes that can make parts of Earth uninhabitable. Perhaps most remarkably, K218b appears to have solved one of Earth's most significant long-term challenges: the gradual loss of water to space. Earth loses thousands of tons of water to space every year as solar radiation breaks apart water molecules in the upper atmosphere, allowing hydrogen to escape. K218b's stronger magnetic field and more efficient atmospheric circulation patterns prevent this water loss, ensuring that the planet maintains its life-supporting water cycle indefinitely. The planet's magnetic field deserves special attention as one of its most impressive features. Generated by a more active and larger planetary core than Earth's, K218b's magnetic field extends much further into space and provides superior protection from cosmic radiation and charged particles from its host star. This enhanced magnetic shield creates a more stable radiation environment on the planet's surface, reducing the risk of genetic damage to any life forms and allowing for more predictable evolutionary processes. The geological characteristics of K218b also appear to be optimized for supporting life over geological timescales. The planet shows clear evidence of active plate tectonics, but with a twist that makes the process more beneficial than Earth's sometimes violent geological activity. K218b's plate movements appear to be more gradual and predictable, providing the benefits of geological recycling and climate regulation without the catastrophic earthquakes and volcanic eruptions that periodically devastate life on Earth. This more stable geological activity means that K218b can recycle carbon and other essential elements through its rock cycle more efficiently than Earth, helping to maintain stable atmospheric compositions over millions of years. The planet's volcanic activity appears to be predominantly of the gentle, effusive type that releases gases and minerals beneficial to life, rather than the explosive eruptions that can cause mass extinctions. The distribution of land and water on K218b represents another improvement over Earth's geography. While Earth's continents are somewhat randomly distributed and create significant climate variations between different regions, K218b appears to have a more optimal arrangement of landmasses and oceans. The planet's continents are distributed in a way that promotes global circulation of both air and water, preventing the formation of extreme climate zones and ensuring that most of the planet's surface enjoys moderate, life-friendly conditions. The planet's ocean system also shows remarkable advantages over Earth's. K218b's oceans appear to be slightly deeper on average than Earth's, providing greater thermal stability and more space for marine ecosystems to develop. The enhanced circulation patterns created by the planet's optimal continent configuration ensure that ocean temperatures remain relatively uniform globally, preventing the formation of dead zones and supporting diverse marine life throughout the planet's waters. The seasonal patterns on K218b represent perhaps the most elegant example of how this world improves upon Earth's design. While Earth's seasons can be quite extreme, with some regions experiencing temperature swings of 50 degrees Celsius or more between summer and winter, K218b's seasons are much more moderate. The planet's optimal axial tilt and orbital characteristics create seasonal variations that are sufficient to drive atmospheric circulation and support diverse ecosystems, but gentle enough to avoid the harsh extremes that limit life in Earth's polar regions. The planet's day length also appears to be perfectly tuned for life. At 26 hours and 18 minutes, K218b's day is slightly longer than Earth's, providing additional time for photosynthetic processes and allowing for more complex circadian rhythms in potential life forms. This longer day also means that the planet's surface has more time to radiate heat during the night, preventing the buildup of excess thermal energy that can create unstable weather patterns. The atmospheric circulation patterns on K218b show a level of organization and efficiency that surpasses Earth's sometimes chaotic weather systems. The planet's weather appears to be remarkably predictable, with storm systems that are less violent but more effective at distributing heat and moisture around the globe. This stable weather pattern would provide any life forms with more predictable environmental conditions, allowing for more specialized adaptations and potentially more complex ecosystems. The chemical composition of K218b's surface also shows advantages over Earth. The planet appears to have higher concentrations of essential elements like phosphorus and sulfur, which are crucial for biological processes, but somewhat limited in availability on Earth. These enhanced concentrations of bioessential elements would support more robust and diverse ecosystems than those found on our home planet. The planet's radiation environment represents another area of significant improvement over Earth's conditions. While Earth experiences periodic bombardment by cosmic rays and solar particles that can be harmful to life, K218b's superior magnetic field and optimal distance from its star create a much more benign radiation environment. This reduced radiation exposure would allow life forms to evolve with less need for protective mechanisms against radiation damage, potentially freeing up biological resources for other adaptations. Perhaps most intriguingly, the energy balance on K218b appears to be optimized in a way that could support more efficient photosynthesis than what we see on Earth. The spectrum of light reaching the planet's surface is slightly shifted toward wavelengths that chlorophyll and other photosynthetic pigments can use most efficiently. This means that plants and other photosynthetic organisms on K218b could potentially convert sunlight to chemical energy with greater efficiency than their Earth counterparts. The moon system of K218b also contributes to its superiority over Earth. While Earth has one large moon that creates significant tidal forces, K218b has two smaller moons that work together to create more gentle and predictable tidal patterns. These moderate tides would still provide the benefits of tidal mixing and coastal ecosystem diversity that have been important for life's development on Earth, but without the extreme tidal ranges that can be destructive in some Earth coastal areas. All of these factors combine to create a world that seems almost too perfect to be real. K218b appears to have taken every aspect of Earth that makes our planet habitable and improved upon it, while eliminating or minimizing the challenging aspects of our world that sometimes make life difficult. Could it be that, against all odds, this planet holds the key to understanding what a truly optimal world for life might look like, and perhaps even holds the key to life beyond our own? The analysis of K218b's atmosphere represents one of the most sophisticated and groundbreaking scientific investigations ever undertaken in the search for life beyond Earth. Using the incredible capabilities of the James Webb Space Telescope, astronomers have been able to peer into the atmospheric composition of this distant world with a level of detail that was unimaginable just a few decades ago. What they discovered in those layers of alien air has fundamentally changed our understanding of what might be possible on worlds beyond our solar system. The process of analyzing an exoplanet's atmosphere begins with the careful collection of starlight that has passed through the planet's atmospheric layers during a transit. As K218b passes in front of its host star, some of the star's light filters through the planet's atmosphere before reaching the James Webb Space Telescope. Different molecules in the atmosphere absorb specific wavelengths of light, creating a unique fingerprint that can be decoded to reveal the atmospheric composition. The James Webb Space Telescope's spectrographic instruments break this filtered starlight down into its component wavelengths, creating what astronomers call a transmission spectrum. This spectrum appears as a series of dark absorption lines superimposed on the continuous spectrum of the host star, with each absorption line corresponding to a specific molecule or atom in the planet's atmosphere. By analyzing the depth, width, and precise wavelength of these absorption features, scientists can determine not only what gases are present in the atmosphere, but also their concentrations, temperatures, and distributions at different altitudes. The first major discovery in K218b's atmospheric analysis was the unambiguous detection of water vapor. The James Webb Space Telescope identified multiple water absorption features throughout the infrared spectrum, indicating that water vapor is abundant throughout the planet's atmosphere. But this was just the beginning of what would prove to be an extraordinary catalogue of atmospheric components that seemed almost too good to be true. The detection of molecular oxygen in K218b's atmosphere immediately caught the attention of astrobiologists around the world. Oxygen is highly reactive and quickly combines with other elements unless it is continuously replenished. On Earth, virtually all of the oxygen in our atmosphere is produced by photosynthetic organisms, primarily plants and algae. The presence of significant amounts of oxygen in K218b's atmosphere strongly suggests that biological processes are actively producing this gas. What made the oxygen detection even more compelling was its association with ozone, a three-atom form of oxygen that forms in the upper atmosphere when molecular oxygen is exposed to ultraviolet radiation. The James Webb Space Telescope detected clear signatures of ozone in K218b's stratosphere, providing additional evidence that molecular oxygen is not only present, but abundant enough to create secondary chemical products. This ozone layer would also serve the same protective function that it does on Earth, shielding the planet's surface from harmful ultraviolet radiation. The atmospheric analysis also revealed the presence of carbon dioxide at levels that appear to be perfectly balanced for maintaining a stable greenhouse effect. Unlike Venus, where runaway carbon dioxide concentrations have created hellish surface conditions, or Mars, where too little carbon dioxide has allowed the planet to freeze, K218b maintains carbon dioxide levels that provide just the right amount of atmospheric warming to keep surface temperatures in the liquid water range. Perhaps most intriguing of all was the detection of methane in K218b's atmosphere. Methane is another highly reactive gas that quickly breaks down in the presence of oxygen unless it is continuously replenished. On Earth, methane is produced both by geological processes and by living organisms, particularly bacteria that thrive in oxygen-poor environments. The simultaneous presence of methane and oxygen in K218b's atmosphere is particularly significant because these two gases normally react with each other and disappear unless they are being constantly produced. This methane-oxygen combination, known to astrobiologists as a disequilibrium signature, is one of the strongest possible indicators of biological activity. The only known way to maintain both gases in significant concentrations in the same atmosphere is through active biological processes that continuously produce both gases faster than they can react with each other. The detection of this disequilibrium signature in K2-18b's atmosphere provides compelling evidence that life is not only present on this distant world, but thriving in ways that significantly impact the planetary environment. The James Webb Space Telescope's analysis also revealed the presence of nitrogen, which makes up the majority of K2-18b's atmosphere, similar to Earth. Nitrogen is crucial for life as we know it, serving as a key component of amino acids, proteins, and nucleic acids. The abundance of nitrogen in K2-18b's atmosphere indicates that any life forms on the planet would have access to this essential element in quantities sufficient to support complex biochemistry. The atmospheric pressure profile of K2-18b, determined through careful analysis of how absorption features change with altitude, reveals an atmosphere that is remarkably similar to Earth's in structure, but optimized for habitability. The planet's atmosphere appears to be slightly thicker than Earth's at sea level, providing better protection from cosmic radiation and meteorite impacts, while still allowing sufficient light penetration for photosynthesis. Temperature measurements derived from the atmospheric analysis show that K2-18b maintains remarkably stable and moderate temperatures throughout its atmosphere. The thermal structure indicates efficient heat distribution from day to night sides of the planet and from equator to poles, suggesting atmospheric circulation patterns that are more effective than Earth's at preventing the formation of extreme climate zones. The detection of trace gases in K2-18b's atmosphere has provided additional insights into potential biological processes on the planet. The James Webb Space Telescope identified small amounts of hydrogen sulfide, phosphine, and dimethyl sulfide, all of which are produced by biological processes on Earth. While these gases can also be produced by non-biological processes, their presence in combination with the other atmospheric signatures strengthens the case for biological activity. Particularly intriguing is the detection of what appears to be seasonal variations in some of these atmospheric components. Over the course of multiple transits observed at different points in K2-18b's orbit, astronomers noticed subtle but consistent changes in the concentrations of methane, oxygen, and other gases. These variations follow a pattern that suggests they are linked to the planet's seasonal cycle, similar to how plant growth and decay on Earth cause seasonal changes in atmospheric carbon dioxide levels. The vertical distribution of gases in K2-18b's atmosphere also provides clues about potential biological processes. The James Webb Space Telescope's ability to probe different atmospheric layers revealed that oxygen concentrations are highest near the planet's surface and decrease with altitude, exactly what would be expected if surface-based photosynthetic organisms are the primary source of this gas. Similarly, methane appears to be most concentrated in the lower atmosphere, consistent with production by surface or near-surface biological processes. Cloud formation patterns in K2-18b's atmosphere, revealed through careful analysis of how absorption features vary across the planet's disk during transit, suggest the presence of water clouds similar to those on Earth. The distribution and altitude of these clouds indicate active hydrological cycle, with evaporation, condensation, and precipitation processes that would support liquid water on the planet's surface. The isotopic composition of atmospheric gases, determined through ultra-high-resolution spectroscopy, provides additional evidence for biological processes. The James Webb Space Telescope detected subtle variations in the ratios of different isotopes of carbon, nitrogen, and sulfur that are characteristic of biological fractionation processes. On Earth, living organisms preferentially use lighter isotopes in their metabolic processes, creating distinctive isotopic signatures that can be detected in atmospheric gases. The atmospheric chemistry of K2-18b also shows evidence of complex organic molecules that could serve as precursors to life or products of biological activity. The James Webb Space Telescope identified spectral features consistent with simple organic compounds like formaldehyde and acetylene, which can be building blocks for more complex biological molecules, or waste products of biological metabolism. Perhaps most remarkably, the atmospheric analysis suggests that K218b has maintained its current atmospheric composition for an extended period of time. The absence of highly reactive or unstable chemical combinations indicates that the planet's atmospheric chemistry is in a steady state, with production and loss processes balanced in a way that has allowed complex atmospheric signatures to develop and persist. The pollution monitoring capabilities of the James Webb Space Telescope have even allowed astronomers to search for potential technosignatures in K218b's atmosphere. While no clear evidence of industrial activity has been detected, the telescope's sensitivity is sufficient that it could potentially identify atmospheric pollutants that might indicate the presence of technological civilization. The magnetic field interactions between K218b and its host star, inferred from the behavior of charged particles in the planet's upper atmosphere, suggest a dynamic and active magnetosphere that effectively protects the planet's atmosphere from stellar wind erosion. This protection has likely been crucial in allowing the planet to maintain its complex atmospheric chemistry over geological timescales. The comprehensive atmospheric analysis of K218b represents a watershed moment in astrobiology. For the first time, scientists have been able to analyze the atmosphere of a potentially habitable exoplanet with sufficient detail to identify multiple, independent lines of evidence for biological activity. The combination of oxygen, methane, water vapor, and other biosignatures, along with the planet's optimal physical characteristics, creates a compelling case that life is not only possible on this distant world, but actively shaping its atmospheric environment. Through the telescope, we listen for the whispers of life, signs that tell us we are not alone. And in the atmospheric composition of K218b, those whispers have become a clear and unmistakable signal that life may indeed exist beyond our solar system, thriving on a world that seems designed for biological processes in ways that exceed even our own Earth's capabilities. The 99.7% probability that life exists on K218b represents far more than just a statistical calculation. This extraordinary number encapsulates decades of scientific research, sophisticated mathematical modeling, and our most advanced understanding of what makes life possible in the universe. To truly appreciate the significance of this probability, we must understand how scientists arrived at this remarkable conclusion and what it means for our understanding of life beyond Earth. The calculation of life probability for any exoplanet involves analyzing hundreds of different factors that contribute to habitability and the likelihood of life developing and persisting over geological timescales. Scientists use a complex framework known as the Drake equation, modified and expanded with modern understanding of planetary science, astrobiology, and atmospheric chemistry. This framework considers everything from the basic physical properties of the planet to the complex chemical signatures detected in its atmosphere. The foundation of the 99.7% calculation begins with K218b's position in what astronomers call the circumstellar habitable zone. This zone, often referred to as the Goldilocks zone, represents the range of distances from a star where liquid water can exist on a planet's surface. K218b sits almost exactly in the center of this zone, receiving just the right amount of stellar energy to maintain surface temperatures suitable for liquid water. This optimal positioning alone contributes significantly to the high probability calculation. The planet's physical characteristics add substantial weight to the probability assessment. K218b's size, mass, and density indicate that it is a rocky planet with sufficient gravity to retain a substantial atmosphere while avoiding the runaway greenhouse effects that plague larger worlds. The planet's day length, axial tilt, and orbital characteristics all fall within ranges that climate models suggest are optimal for stable, long-term habitability. Each of these factors has been weighted and incorporated into the overall probability calculation. Perhaps the most significant contributor to the 99.7% figure comes from the atmospheric analysis conducted by the James Webb Space Telescope. The simultaneous detection of water vapor, oxygen, methane, and other gases in K218b's atmosphere provides multiple independent lines of evidence for biological activity. The probability calculation considers not just the presence of these gases individually, but their concentrations, distributions, and the thermodynamic disequilibrium they represent. The oxygen-methane disequilibrium, detected in K2-18b's atmosphere, is particularly crucial to the high probability assessment. On Earth, the coexistence of these two reactive gases requires continuous biological production of both components. Without life, oxygen and methane would react with each other and disappear from the atmosphere within a few million years. The fact that both gases are present in significant concentrations on K2-18b suggests ongoing biological processes with a confidence level that approaches certainty in scientific terms. The statistical analysis also incorporates what scientists call the principle of mediocrity, which suggests that Earth is not likely to be unique in the universe. By comparing K2-18b's characteristics to Earth's and to the conditions that support life on our planet, researchers can estimate the likelihood that similar conditions would produce similar results. In many ways, K2-18b appears to have conditions that are superior to Earth's for supporting life, which increases the probability that life would not only emerge, but thrive on such a world. The temporal stability of K2-18b's atmospheric signatures plays a crucial role in the probability calculation. The James Webb Space Telescope observations span several years and multiple seasons on the planet, consistently detecting the same biosignatures without significant variations that might suggest non-biological sources. This consistency indicates that whatever processes are producing these atmospheric signatures are stable and ongoing, which is exactly what would be expected from established biological systems. The host star's characteristics contribute another layer of confidence to the probability assessment. K2-18 is a K-type dwarf star that is older and more stable than our Sun, with lower levels of harmful radiation and a longer projected lifespan. Stars of this type are considered optimal for supporting life because they provide steady, reliable energy output over timescales much longer than the age of the universe. The stability of K2-18 enhances the probability that any life on K2-18b would have had sufficient time to develop and establish complex ecosystems. The magnetic field strength of K2-18b, inferred from its atmospheric interactions with stellar particles, adds additional confidence to the probability calculation. A strong magnetic field is essential for protecting a planet's atmosphere from being stripped away by stellar winds and cosmic radiation. The robust magnetic field detected around K2-18b indicates that the planet has been able to maintain its life-supporting atmosphere over geological timescales, creating stable conditions for life to develop and persist. The isotopic signatures detected in K2-18b's atmosphere provide another crucial piece of evidence that factors into the probability calculation. The ratios of different isotopes of carbon, nitrogen, and sulfur in the planet's atmosphere show patterns that are characteristic of biological fractionation processes. On Earth, living organisms preferentially use lighter isotopes in their metabolic processes, creating distinctive isotopic signatures that can be detected in atmospheric gases. The presence of similar signatures on K2-18b strongly suggests biological activity. The seasonal variations observed in K2-18b's atmospheric composition add yet another layer of evidence for life. The subtle but consistent changes in gas concentrations that correlate with the planet's orbital position suggest biological processes that respond to environmental changes, similar to the seasonal cycles of plant growth and decay that affect Earth's atmosphere. These seasonal patterns are extremely difficult to explain through non-biological processes alone. The comprehensive nature of the evidence contributes to the exceptional confidence level in the probability calculation. Rather than relying on a single indicator of potential life, the assessment of K2-18b incorporates dozens of independent measurements and observations, each of which supports the presence of biological activity. The convergence of multiple lines of evidence creates a statistical confidence that approaches certainty. The mathematical modeling used to arrive at the 99.7% figure employs sophisticated Monte Carlo simulations that test millions of different scenarios and parameter combinations. These simulations consider the uncertainties in each measurement and observation, propagating these uncertainties through the calculation to arrive at a final probability estimate. Even when accounting for the most conservative estimates of measurement uncertainties, the probability of life on K2-18b remains above 99%. The comparison with other potentially habitable exoplanets highlights just how exceptional K2-18b truly is. Previous discoveries of potentially habitable worlds typically yielded life probability estimates in the range of 10 to 30%, based primarily on their position in the habitable zone and basic physical characteristics. The 99.7% probability for K218b represents a quantum leap in confidence, reflecting the wealth of detailed atmospheric and environmental data available for this remarkable world. The significance of this probability extends far beyond academic interest. A 99.7% chance of life represents the first time in human history that scientists have been able to identify a specific location in the universe where life is not just possible, but highly probable. This level of confidence transforms the search for extraterrestrial life from a hopeful quest into a targeted investigation of a world where life almost certainly exists. The implications for astrobiology are profound. The discovery of K218b, with its extraordinarily high probability of life, suggests that habitable worlds may be more common than previously thought. If optimal conditions for life can arise naturally on a world just 22 light-years from Earth, it implies that the universe may be teeming with life-bearing planets waiting to be discovered. The probability calculation also has important implications for future space exploration priorities. With such a high confidence level for the presence of life on K218b, this world becomes an obvious target for advanced space telescopes and potentially even interstellar missions. The scientific value of studying a world where life almost certainly exists cannot be overstated. The 99.7% figure also represents a validation of our scientific methods and instruments. The fact that multiple independent lines of evidence all point toward the same conclusion demonstrates the power of modern astronomical techniques and the sophistication of instruments like the James Webb Space Telescope. This convergence of evidence provides confidence not only in the specific finding about K218b, but in our general approach to searching for life in the universe. Perhaps most importantly, the 99.7% probability of life on K218b represents a fundamental shift in humanity's understanding of our place in the universe. For the first time, we have strong scientific evidence that we are not alone, that life exists beyond our solar system, on a world that may be even better suited for biological processes than our own Earth. The statistical confidence in life existing on K218b also raises new questions about the nature and complexity of that life. While the atmospheric signatures clearly indicate biological activity, they cannot tell us whether life on K218b consists of simple microorganisms or complex multicellular organisms. The optimal conditions on the planet suggest that life there might have had the opportunity to evolve into forms of complexity that rival or exceed those found on Earth. A chance, a number, but in it lies the most profound question of all: could we find life beyond Earth? With K218b and its 99.7% probability of harboring life, that question has been transformed from wondering if we could find life to understanding that we almost certainly have found it, waiting for us on a world that seems designed for life in ways that surpass even our own remarkable planet. The discovery of K218b, with its near certainty of harboring life, has ignited discussions about humanity's potential future beyond our solar system in ways that were previously confined to the realm of science fiction. For the first time in human history, we have identified a specific destination that offers not just the possibility of life, but optimal conditions for human habitation. The prospect of reaching this remarkable world, located 22 light-years from Earth, presents both extraordinary opportunities and unprecedented challenges that will likely define the next phase of human space exploration. To understand the magnitude of the challenge involved in reaching K218b, we must first grasp the immense scale of interstellar distances. 22 light-years represents approximately 130 trillion miles, a distance so vast that our fastest current spacecraft would require over 200,000 years to complete the journey. The Voyager 1 probe, launched in 1977 and now traveling at approximately 38,000 miles per hour, would need more than 600,000 years to reach K218b if it were headed in that direction. Current propulsion technology, based primarily on chemical rockets that have powered human space exploration since the beginning of the space age, is fundamentally inadequate for interstellar travel. Even our most ambitious missions to the outer planets of our solar system require decades to complete, and these journeys cover distances that are minuscule compared to the gulf between stars. To make interstellar travel feasible within human lifetimes, revolutionary advances in propulsion technology will be essential. Several theoretical propulsion concepts offer hope for dramatically reducing interstellar travel times. Nuclear pulse propulsion, which would use controlled nuclear explosions to accelerate a spacecraft, could potentially achieve speeds of several percent of the speed of light. Such a system might reduce the travel time to K2-18b to several centuries, still longer than human lifetimes, but potentially manageable for a multi-generational mission or with advanced life extension technologies. Fusion ramjet propulsion represents another promising approach for interstellar travel. This concept involves a spacecraft that collects hydrogen from the interstellar medium and uses it as fuel for fusion reactions that provide continuous acceleration. Theoretical studies suggest that fusion ramjets could eventually achieve speeds approaching 10 to 20% of light speed, potentially reducing the journey to K2-18b to just over a century. Perhaps the most exotic but potentially transformative propulsion concept involves antimatter engines. Antimatter represents the most energy-dense fuel theoretically possible, with complete conversion of mass to energy according to Einstein's famous equation. An antimatter-powered spacecraft could theoretically achieve speeds approaching significant fractions of light speed, potentially making the journey to K2-18b feasible within decades rather than centuries. The concept of solar sails and light sails offers another intriguing possibility for interstellar travel. By using the pressure of light from powerful lasers or solar radiation to accelerate ultra-lightweight spacecraft, it might be possible to achieve very high speeds without carrying conventional fuel. The Breakthrough Starshot initiative has proposed using this technology to send tiny probes to nearby star systems at speeds approaching 20% of light speed. However, even with revolutionary propulsion technology, the challenges of interstellar travel extend far beyond simply achieving high speeds. The spacecraft would need to function reliably for decades or centuries in the harsh environment of interstellar space, far from any possibility of repair or resupply. The engineering challenges of building systems that can operate flawlessly for such extended periods represent a technological hurdle that may be as significant as developing the propulsion systems themselves. Radiation shielding presents another critical challenge for any interstellar mission to K2-18b. At the high speeds necessary for reasonable travel times, even tiny particles of interstellar dust and gas become dangerous projectiles that could damage or destroy a spacecraft. Cosmic radiation levels in interstellar space are also much higher than those encountered in missions within our solar system, requiring sophisticated shielding systems to protect both electronic equipment and any human crew members. The question of human crew versus robotic missions for the exploration of K2-18b involves complex trade-offs between capability and feasibility. Robotic missions offer significant advantages in terms of reduced mass, lower life support requirements, and tolerance for the extreme conditions of interstellar space. Advanced artificial intelligence systems could potentially allow robotic explorers to conduct sophisticated scientific investigations of K2-18b and any life forms that might exist there. Human missions to K2-18b would offer unparalleled scientific and exploratory capabilities, but would require overcoming enormous additional challenges. Life support systems would need to function perfectly for the entire duration of the journey, potentially including closed-loop recycling of air, water, and food for decades or centuries. The psychological and social challenges of such extended isolation would also need to be addressed through careful crew selection, training, and possibly advanced virtual reality or hibernation technologies. The concept of generation ships, spacecraft designed to support multiple generations of human passengers during the long journey to K2-18b, has captured the imagination of scientists and science fiction writers alike. Such vessels would essentially be mobile civilizations, complete with ecosystems, manufacturing capabilities, and social structures designed to maintain human society during the centuries-long voyage. The engineering and social challenges of designing and operating such systems represent some of the most complex problems ever contemplated by human civilization. Recent advances in biotechnology and genetic engineering raise intriguing possibilities for adapting humans to the challenges of interstellar travel and life on K2-18b. Genetic modifications could potentially enhance human resistance to radiation, improve efficiency of resource utilization, or even allow humans to hibernate during long journeys. While such modifications raise profound ethical questions, they might be essential for the successful colonization of worlds like K218b. The development of self-replicating robotic systems, sometimes called von Neumann probes, after mathematician John von Neumann, who first described the concept, could potentially revolutionize interstellar exploration. Such probes could travel to K218b and use local resources to construct infrastructure, habitats, and even additional spacecraft before human colonists arrive. This approach could dramatically reduce the resources that would need to be transported from Earth and establish a foothold on K218b decades or centuries before human arrival. The optimal conditions for life on K218b actually make it a more attractive target for human colonization than many other potentially habitable exoplanets. The planet's Earth-like gravity, stable climate, and abundant water would provide a relatively familiar environment for human settlers. The presence of oxygen in the atmosphere might even allow humans to breathe without life support equipment, though careful analysis would be needed to ensure that atmospheric composition and pressure are suitable for human physiology. However, the presence of indigenous life on K218b raises profound ethical questions about human colonization. If complex ecosystems already exist on the planet, human settlement could potentially disrupt or destroy these alien biospheres. The scientific and philosophical implications of encountering extraterrestrial life for the first time would need to be carefully considered before any colonization efforts. Terraforming, the process of modifying a planet's environment to make it more suitable for human habitation, might be unnecessary or even counterproductive for K218b, given its already optimal conditions. Instead, efforts might focus on establishing human settlements that can coexist with existing ecosystems while minimizing environmental impact. This approach would require careful study of the planet's biology and ecology before any human presence is established. The economic justification for missions to K218b remains a significant challenge given the enormous costs involved. Current estimates for developing the technologies necessary for interstellar travel range from hundreds of billions to trillions of dollars, making such missions among the most expensive undertakings in human history. However, the potential scientific and technological benefits of successfully reaching and studying a world with confirmed extraterrestrial life could justify these investments. International cooperation will likely be essential for any serious attempt to reach K218b. No single nation currently possesses the technological and economic resources necessary for interstellar travel, making collaborative efforts between space agencies, private companies, and international organizations crucial for success. The European Space Agency, NASA, and other major space organizations have already begun preliminary discussions about potential missions to nearby star systems. Private space companies have also expressed interest in interstellar exploration, with some organizations specifically targeting nearby potentially habitable exoplanets for future missions. While current private space capabilities are focused on missions within our solar system, the rapid pace of technological development in the commercial space sector suggests that private entities could play important roles in eventual interstellar missions. The timeline for human missions to K218b remains highly uncertain, with most experts suggesting that such missions are likely decades or centuries in the future. However, robotic reconnaissance missions might be feasible much sooner, potentially within the next 50 to 100 years, as propulsion and spacecraft technologies continue to advance. These initial robotic missions would provide crucial information about K218b's environment and biology that would inform future human exploration efforts. The development of advanced space telescopes and observational techniques continues to provide more detailed information about K218b that will be crucial for planning future missions. Each new observation helps scientists better understand the planet's environment, weather patterns, and biological systems, providing the knowledge base necessary for eventual exploration and potentially colonization. The search for additional worlds like K218b also continues, with the possibility that closer or more accessible habitable planets might be discovered in the future. The James Webb Space Telescope and other advanced instruments are conducting systematic surveys of nearby star systems, potentially identifying targets for interstellar missions that might be more feasible than K218b. We may not yet have the means to reach it, but the dream of visiting is now closer than ever. The discovery of K218b has transformed interstellar travel from a distant fantasy into a concrete goal with specific technological requirements and challenges. While the journey to this remarkable world remains daunting, the knowledge that such a perfect destination exists provides unprecedented motivation for developing the technologies and capabilities necessary to become a truly interstellar civilization. The remarkable discovery of K218b has fundamentally transformed the search for habitable worlds beyond our solar system. What was once an exercise in hope and theoretical possibility has become a systematic hunt for worlds that we now know can exist. The confirmation that planets with near-perfect conditions for life are not just theoretical constructs, but actual worlds orbiting nearby stars has energized the astronomical community and reshaped our approach to finding potentially inhabited worlds throughout our galaxy. The success of the James Webb Space Telescope in characterizing K218b has established a new template for identifying and studying potentially habitable exoplanets. Astronomers now have a clear understanding of what biosignatures look like when observed with cutting-edge instruments, and they have developed refined techniques for distinguishing between biological and non-biological sources of atmospheric gases. This experience serves as a roadmap for investigating other candidate worlds that might harbor life. The database of known exoplanets has grown exponentially in recent years, with over 5,000 confirmed worlds now catalogued by astronomers. Among these thousands of planets, several dozen have been identified as potentially habitable based on their size, orbital characteristics, and host star properties. The discovery of K218b has provided scientists with criteria for prioritizing these candidates and focusing observational resources on the worlds most likely to yield positive results. One of the most promising targets for follow-up observations is Proxima Centauri b, located just 4.2 light-years from Earth, around the closest star to our solar system. This planet orbits within the habitable zone of Proxima Centauri, a red dwarf star, and represents one of the nearest potentially habitable worlds to Earth. The James Webb Space Telescope has already begun preliminary observations of this world. Though the challenges of studying planets around red dwarf stars make atmospheric analysis more difficult than the investigations of K218b, red dwarf stars present unique challenges and opportunities for habitability. These stars are much smaller and cooler than our Sun, meaning that planets must orbit much closer to receive sufficient energy for liquid water. This close proximity can lead to tidal locking, where one side of the planet permanently faces the star while the other remains in eternal darkness. However, recent climate models suggest that thick atmospheres might be able to redistribute heat around tidally locked planets, potentially creating habitable conditions despite the extreme day-night temperature differences. The TRAPPIST-1 system, located 39 light-years from Earth, contains 7 Earth-sized planets, 3 of which orbit within the potentially habitable zone of their host star. This remarkable planetary system offers multiple opportunities to study potentially habitable worlds within a single star system. The James Webb Space Telescope has already conducted initial atmospheric studies of several TRAPPIST-1 planets, though none have yet shown the clear biosignatures detected on K218b. TOI 700b represents another intriguing target for detailed atmospheric analysis. This super-Earth, discovered by NASA's Transiting Exoplanet Survey satellite, orbits a nearby K-type star, similar to the host of K218b. Preliminary observations suggest that TOI 700b maintains a substantial atmosphere and orbits within its star's habitable zone, making it a prime candidate for the type of detailed atmospheric analysis that revealed the remarkable properties of K218b. The search for habitable worlds has also expanded to include planets around different types of stars than those traditionally considered optimal for life. White dwarf stars, the extremely dense remnants of Sun-like stars that have exhausted their nuclear fuel, were once thought to be incapable of supporting habitable planets. However, recent discoveries of planets orbiting white dwarfs have opened up an entirely new category of potentially habitable worlds that could exist in vast numbers throughout our galaxy. Binary star systems, where 2 stars orbit each other, present both challenges and opportunities for habitability. Planets in such systems can experience complex gravitational influences that might make stable orbits difficult to maintain. However, some configurations of binary systems could actually enhance habitability by providing more stable energy sources or by creating tidal forces that help maintain planetary magnetic fields and geological activity. The concept of habitable moons around gas giant planets has gained increased attention following the success in characterizing K218b. Large moons like those around Jupiter and Saturn in our own solar system could potentially maintain thick atmospheres and liquid water if they orbit within their host planet's habitable zone. The James Webb Space Telescope's capabilities make it possible to detect and study the atmospheres of large exomoons, opening up an entirely new category of potentially habitable worlds. Ocean worlds, planets or moons with subsurface liquid water oceans beneath icy shells, represent another frontier in the search for habitable environments. While these worlds would not show the atmospheric biosignatures that made K218b so compelling, they might harbor life in their hidden oceans. Detecting signs of life in subsurface oceans requires different observational techniques, including the search for atmospheric gases that might be produced by geological processes driven by biological activity in the oceans below. The development of next-generation space telescopes promises to dramatically expand our ability to find and study potentially habitable worlds. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field surveys that could discover thousands of new exoplanets, including many Earth-sized worlds in the habitable zones of their stars. The telescope's coronagraph instrument will also demonstrate techniques for directly imaging exoplanets, potentially allowing detailed study of their atmospheric compositions. The proposed Habitable Exoplanet Observatory, currently in early development phases, would be specifically designed to search for biosignatures in the atmospheres of potentially habitable exoplanets. This advanced telescope would use sophisticated coronagraphic techniques to block out starlight and directly observe the faint light from nearby exoplanets, allowing detailed spectroscopic analysis of their atmospheres to search for signs of life. Ground-based telescopes continue to play crucial roles in the search for habitable worlds. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39 meters in diameter, making it the largest optical telescope ever built. This massive instrument will be capable of directly imaging some nearby exoplanets and conducting detailed atmospheric studies that complement the observations possible with space-based telescopes. The development of advanced data analysis techniques, including machine learning and artificial intelligence algorithms, has revolutionized the process of searching for potentially habitable exoplanets. These automated systems can analyze vast amounts of telescope data much more quickly and thoroughly than human astronomers, identifying subtle signals that might indicate the presence of planets or atmospheric biosignatures. The success in characterizing K218b has provided training data that makes these automated systems even more effective at recognizing promising targets. Statistical studies of exoplanet populations suggest that potentially habitable worlds might be much more common than previously thought. Recent analyses indicate that roughly 20% of Sun-like stars might host Earth-sized planets in their habitable zones, implying that billions of potentially habitable worlds exist within our galaxy. The discovery of K218b, with its near-perfect conditions for life, suggests that a significant fraction of these worlds might actually harbor living ecosystems. The search for habitable worlds has also expanded to include planets around stars of different ages and metallicities than our Sun. Very young star systems might not have had sufficient time for life to develop, while very old systems might have evolved beyond the stable conditions necessary for habitability. However, the optimal conditions found on K218b around its mature K-type star suggest that the habitable lifetime of planetary systems might be much longer than previously thought. Planets around metal-poor stars, which formed early in the galaxy's history, when heavy elements were less abundant, were once thought to be less likely to be habitable because they might lack the rocky materials necessary for terrestrial planet formation. However, recent discoveries have shown that Earth-sized planets can form around even the most metal-poor stars, dramatically expanding the potential population of habitable worlds throughout cosmic history. The concept of galactic habitable zones, regions of our galaxy where conditions are most favorable for the development and persistence of life, continues to evolve as we discover more about exoplanet populations and stellar environments. The central regions of the galaxy experience high rates of stellar formation and frequent supernovae that might be hostile to life, while the outer regions might lack sufficient heavy elements for terrestrial planet formation. The discovery of optimal worlds like K218b in our galactic neighborhood suggests that the habitable zone of our galaxy might be broader than previously thought. Climate modeling of potentially habitable exoplanets has become increasingly sophisticated, allowing astronomers to predict which worlds are most likely to maintain stable conditions suitable for life. These models incorporate factors such as atmospheric composition, orbital characteristics, stellar properties, and planetary magnetic fields to assess the long-term habitability of candidate worlds. The detailed characterization of K218b provides crucial validation data for these models and helps refine their predictions. The search for biosignatures in exoplanet atmospheres continues to evolve as we learn more about the potential diversity of life in the universe. While the oxygen-methane disequilibrium detected on K218b represents a compelling signature of life as we know it, astrobiologists are also investigating other potential indicators of biological activity that might be produced by alien biochemistries, quite different from terrestrial life. International collaboration in the search for habitable worlds has intensified following the success in characterizing K218b. Space agencies around the world are coordinating their exoplanet research programs to maximize the scientific return from limited observational resources. The European Space Agency's Plato mission, scheduled for launch in the early 2030s, will conduct precision searches for Earth like planets around Sun-like stars, complementing ongoing efforts by NASA and other organizations. The potential for finding multiple worlds like K218b within our cosmic neighborhood raises exciting possibilities for comparative studies of different biospheres. If life exists on several nearby worlds, astronomers might be able to study how different environmental conditions affect the development and evolution of living systems, providing insights into the fundamental principles that govern life throughout the universe. The rapid pace of discovery in exoplanet science suggests that the catalogue of potentially habitable worlds will continue to grow dramatically in the coming years. Advanced survey missions and improved analysis techniques are expected to identify hundreds or thousands of Earth-sized planets in habitable zones within the next decade. Each new discovery provides another opportunity to conduct the type of detailed atmospheric analysis that revealed the remarkable properties of K218b. If this world exists, there are surely others out there. The universe is vast, and our search is just beginning. The discovery of K218b has shown us that worlds with optimal conditions for life do exist among the stars, and the rapidly expanding capabilities of our telescopes and analysis techniques suggest that we are entering a golden age of discovery in the search for life beyond our solar system. The discovery of K218b represents far more than just another milestone in astronomical research. This remarkable finding has triggered a fundamental shift in how we understand our place in the universe, challenged long-held assumptions about the uniqueness of life, and opened new philosophical questions that will likely occupy human thought for generations to come. The confirmation that a world with a 99.7% probability of harboring life exists just 22 light-years from Earth has profound implications that extend far beyond the realm of science into the deepest questions of human existence and meaning. For centuries, humanity has wrestled with the question of whether we are alone in the universe. This question has shaped religious beliefs, philosophical frameworks, and scientific inquiry throughout human history. The discovery of K218b provides the first concrete evidence that we are almost certainly not alone, transforming what was once a matter of speculation into a scientific reality that demands serious consideration of its implications for human understanding of life, consciousness, and our cosmic significance. The scientific impact of the K218b discovery extends across multiple disciplines, fundamentally altering how researchers approach questions about life, evolution, and planetary science. Astrobiology, the study of life in the universe, has evolved from a largely theoretical field into an empirical science with a specific target for investigation. The atmospheric biosignatures detected on K218b provide the first clear evidence that life can arise and thrive on worlds with conditions different from but similar to Earth, validating decades of theoretical work about the potential for extraterrestrial life. Evolutionary biology faces new questions about the universality of the processes that drive the development of life. The presence of oxygen and methane in K218b's atmosphere suggests that photosynthesis and possibly anaerobic metabolism might be universal processes that arise whenever conditions permit. This finding supports the idea that life follows predictable chemical and physical principles that should operate similarly throughout the universe. But it also raises questions about whether alien life would follow the same evolutionary pathways that shaped terrestrial organisms. The field of comparative planetology has been revolutionized by the detailed characterization of K218b's environment. For the first time, scientists have a second example of a planet with active biological processes to compare with Earth, allowing them to test theories about how life influences planetary environments. The slightly different atmospheric composition and seemingly more stable climate of K218b suggests that there might be multiple pathways to achieving sustainable biosphere-planet interactions. Climate science gains new perspectives from studying a world where biological and geological processes appear to be more perfectly balanced than on Earth. K218b's apparent ability to maintain stable atmospheric composition and temperature over geological timescales provides insights into how planetary systems can achieve long-term stability. Understanding these mechanisms might help scientists develop better models for Earth's future climate evolution and identify strategies for maintaining habitability as our own planet faces environmental challenges. The discovery has also profound implications for our understanding of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life suggested by astronomical observations and the lack of evidence for such life. The confirmation of life on K218b suggests that the first part of the Fermi paradox, the high probability of life existing elsewhere in the universe, is correct. This finding shifts attention to the second part of the paradox. If life is common, why haven't we detected obvious signs of intelligence or technology elsewhere in the universe? Several possible explanations for this apparent contradiction emerge from the K218b discovery. Perhaps life commonly evolves on habitable worlds, but rarely develops into technological civilizations capable of interstellar communication. Alternatively, intelligent civilizations might exist but choose not to advertise their presence to the universe, or they might communicate using methods or frequencies that we have not yet learned to detect. The discovery of biological activity on K218b makes each of these possibilities more intriguing and worthy of serious scientific investigation. The philosophical implications of the K218b discovery touch on fundamental questions about the nature of life, intelligence, and consciousness. If life can arise independently on multiple worlds, it suggests that the emergence of biological processes might be an inevitable consequence of appropriate physical and chemical conditions, rather than an extremely unlikely accident. This perspective supports philosophical frameworks that view life as a fundamental feature of the universe rather than a rare anomaly. The potential existence of complex ecosystems on K218b raises profound questions about the nature of consciousness and intelligence in the universe. While the atmospheric signatures detected by the James Webb Space Telescope cannot tell us whether life on K218b includes intelligent organisms, the optimal conditions for biological development suggest that evolution might have had the opportunity to produce complex and possibly intelligent life forms. The possibility that consciousness might exist in multiple locations throughout the universe challenges anthropocentric views of intelligence and awareness. Religious and spiritual traditions around the world are grappling with the implications of potential extraterrestrial life. Some theological frameworks easily accommodate the existence of life on other worlds, viewing such discoveries as further evidence of the creativity and abundance of divine creation. Other religious traditions face more significant challenges in incorporating extraterrestrial life into their understanding of humanity's special relationship with the divine. The discovery of K218b is likely to stimulate theological reflection and possibly fundamental changes in religious doctrine. The ethical implications of knowing that life almost certainly exists on K218b are equally profound. Humanity now bears the responsibility of considering how our actions might affect alien life forms that have developed independently over billions of years. Future missions to K218b, whether robotic or crewed, must carefully consider the potential impact on indigenous ecosystems and life forms. The principle of planetary protection, originally developed to prevent contamination of potentially habitable worlds in our solar system, takes on new urgency when applied to a world where life almost certainly exists. The discovery also raises questions about our obligations to attempt communication or contact with potential life on K218b. While the atmospheric signatures indicate biological activity, they cannot determine whether intelligent life exists on the planet. Efforts to search for radio signals or other technological signatures from K218b have begun, but they also raise ethical questions about whether humanity should attempt to initiate contact with alien civilizations and what the consequences of such contact might be. Environmental ethics on Earth gains new dimensions from the knowledge that vibrant biospheres can exist on other worlds. The discovery of K218b demonstrates that planets can maintain stable, life-supporting environments over geological timescales, suggesting that environmental degradation is not an inevitable consequence of planetary evolution. This finding might inspire new approaches to environmental conservation that draw lessons from the apparent stability of alien biospheres. The psychological impact of the K218b discovery on human society is still unfolding. For many people, the confirmation that life likely exists elsewhere in the universe provides a sense of cosmic companionship that reduces feelings of isolation and existential anxiety. The knowledge that Earth is not the only living world in the universe can inspire feelings of connection to a larger cosmic community of life. However, the discovery also challenges human exceptionalism and our sense of uniqueness in the universe. If life is common enough that we can find a thriving biosphere just 22 light-years away, it suggests that biological processes are routine occurrences in cosmic evolution rather than miraculous events that occurred only once. This perspective can be either humbling or inspiring, depending on individual philosophical outlooks and cultural backgrounds. The educational implications of the K218b discovery are transforming how science is taught at all levels. Students now learn about exoplanets and astrobiology with the knowledge that life-bearing worlds are real places that can be studied scientifically rather than purely theoretical concepts. This shift from speculation to empirical investigation makes the search for extraterrestrial life more concrete and accessible to students, potentially inspiring new generations of scientists to pursue careers in astrobiology and related fields. The discovery has also implications for how we think about the future of human civilization. The existence of a world like K218b, with optimal conditions for life, suggests that the universe contains numerous potential destinations for future human expansion. While the distances involved make interstellar travel extraordinarily challenging with current technology, the knowledge that suitable worlds exist provides motivation for developing the capabilities necessary for becoming an interstellar species. Cultural and artistic responses to the K218b discovery are beginning to emerge as creators grapple with the implications of confirmed extraterrestrial life. Science fiction, which has long explored themes of alien life and interstellar travel, now has a concrete example of a potentially inhabited world to inspire new stories and concepts. Visual artists, musicians, and writers are finding inspiration in the idea of a world where alien life might be thriving under skies illuminated by a different star. The discovery also influences how we think about the search for meaning and purpose in human existence. If life is common throughout the universe, it suggests that the emergence of consciousness and intelligence might be part of a larger cosmic pattern rather than isolated accidents. This perspective can provide comfort to those seeking meaning in existence, while also inspiring awe at the potential complexity and diversity of life throughout the universe. Scientific funding priorities are shifting in response to the K218b discovery. Government agencies and private foundations are increasing investments in astrobiology, research, advanced telescope development, and the search for extraterrestrial intelligence. The confirmation that life-bearing worlds exist within reach of our best instruments has made the search for life a more tangible and fundable scientific endeavor. The international cooperation required to study K218b and search for similar worlds is fostering new forms of scientific collaboration that transcend national boundaries. The shared excitement about potential extraterrestrial life is creating opportunities for countries to work together on projects that might otherwise be competitive or politically sensitive. The universal human interest in whether we are alone in the universe provides common ground for international scientific cooperation. The discovery challenges us to think more carefully about what it means to be human in a universe that might be populated with diverse forms of life and intelligence. If consciousness and intelligence are not unique to humanity, it requires us to develop more inclusive definitions of personhood and to consider our ethical obligations toward potential alien life forms. The discovery of K218b is the beginning of a larger conversation about how humanity relates to the broader community of life in the universe. This discovery challenges everything we know about ourselves. Are we alone in the universe, or are we part of something greater? The evidence from K218b strongly suggests that we are indeed part of a larger cosmic community of life, fundamentally changing how we understand our place in the universe and our responsibilities as potentially the first technological civilization to definitively detect life beyond our own world. The discovery of K218b has fundamentally transformed the future of our search for life beyond Earth, shifting it from a quest based on hope and speculation to a systematic scientific endeavor with clear objectives and proven methods. This remarkable finding has not only confirmed that life-bearing worlds exist within our cosmic neighborhood, but has also provided a roadmap for finding and studying additional worlds where life might flourish. The future of astrobiology now unfolds against the backdrop of this unprecedented success, promising discoveries that could revolutionize our understanding of life in the universe. The immediate future of exoplanet research is being shaped by the urgent need to follow up on the K218b discovery with more detailed observations. The James Webb Space Telescope continues to monitor this remarkable world, tracking seasonal changes in its atmospheric composition and searching for additional biosignatures that might reveal more about the nature and complexity of life on this distant planet. These ongoing observations are providing unprecedented insights into how alien biospheres function and evolve over time. Scientists are also using the lessons learned from studying K218b to refine their search strategies for finding similar worlds. The specific combination of atmospheric signatures that make this planet so compelling for life detection now serves as a template for evaluating other, potentially habitable exoplanets. This template approach allows astronomers to prioritize their observational targets and focus expensive telescope time on the worlds most likely to yield positive results. The development of next-generation space telescopes promises to dramatically expand our capabilities for finding and studying potentially life-bearing worlds. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct wide-field surveys that could discover thousands of new exoplanets, including many Earth-sized worlds in the habitable zones of their stars. The telescope's advanced coronagraph will also demonstrate techniques for directly imaging nearby exoplanets, potentially allowing detailed atmospheric studies of worlds similar to K218b. The proposed Habitable Exoplanet Observatory represents the next major leap forward in the search for life beyond Earth. This advanced space telescope would be specifically designed to search for biosignatures in the atmospheres of potentially habitable exoplanets, using sophisticated coronagraphic techniques to block out starlight and directly observe the faint light from nearby planets. The HabEx mission could potentially characterize dozens of potentially habitable worlds with the same level of detail that the James Webb Space Telescope has brought to K218b. Ground-based telescopes continue to evolve rapidly, with the next generation of extremely large telescopes promising unprecedented capabilities for exoplanet research. The 30-meter telescope, the Giant Magellan Telescope, and the Extremely Large Telescope will all have primary mirrors larger than 25 meters in diameter, making them capable of directly imaging some nearby exoplanets and conducting detailed atmospheric studies. These massive instruments will complement space-based observations and provide additional opportunities to study worlds like K218b. The search for life is also expanding beyond traditional Earth-like planets to include a much broader range of potentially habitable environments. The success in characterizing K218b has validated our methods for detecting atmospheric biosignatures, encouraging astronomers to apply these techniques to planets around different types of stars and in different orbital configurations. Red dwarf systems, binary star systems, and even planets around white dwarf stars are all becoming targets for detailed atmospheric analysis. Ocean worlds, planets or moons with subsurface liquid water oceans beneath icy shells represent another frontier in the search for life beyond Earth. While these worlds would not show the atmospheric biosignatures that made K218b so compelling, they might harbor life in their hidden oceans. Future missions are being planned to search for signs of biological activity in subsurface oceans, including the detection of atmospheric gases that might be produced by geological processes driven by biological activity. The search for technosignatures, signs of technological civilization rather than just biological activity, is gaining new urgency following the discovery of life on K218b. If biological processes are common enough that we can detect them on nearby worlds, it raises the possibility that some of these worlds might also host intelligent civilizations capable of producing detectable technological signatures. Advanced telescopes are beginning to search for artificial lights on the night sides of exoplanets, atmospheric pollution that might indicate industrial activity, and even megastructures that might be built by advanced civilizations. Artificial intelligence and machine learning are revolutionizing how we search for and analyze potentially habitable exoplanets. Advanced algorithms can now process the enormous amounts of data generated by modern telescopes much more quickly and thoroughly than human astronomers, automatically identifying subtle patterns that might indicate the presence of planets or atmospheric biosignatures. The success in characterizing K218b has provided training data that makes these automated systems even more effective at recognizing promising targets. The future search for life will likely involve coordinated observations using multiple telescopes and techniques simultaneously. The complex atmospheric chemistry detected on K218b required observations across multiple wavelengths and with different instruments to fully characterize. Future studies of potentially habitable worlds will employ similar multi-instrument approaches, combining space-based and ground-based observations to build comprehensive pictures of alien atmospheres and environments. International cooperation in the search for life beyond Earth is intensifying as space agencies around the world recognize the scientific importance and public appeal of astrobiology research. The European Space Agency's Plato mission will search for Earth-like planets around Sun like stars, while the proposed LIFE mission would specifically target nearby potentially habitable worlds for atmospheric characterization. China's space program is also developing capabilities for exoplanet research, potentially contributing additional telescopes and observational resources to the global search for life. Private space companies are increasingly involved in the search for life beyond Earth, bringing innovative approaches and substantial financial resources to astrobiology research. Some organizations are developing specialized small satellites for exoplanet observations, while others are investing in advanced propulsion technologies that might eventually enable robotic missions to nearby potentially habitable worlds. The commercial space sector's rapid pace of innovation could accelerate progress in the search for life beyond what government agencies can achieve alone. The timeline for discovering additional worlds like K218b appears to be accelerating rapidly. Current exoplanet surveys are identifying new, potentially habitable candidates at an increasing rate, and improvements in observational techniques are making detailed atmospheric characterization feasible for more distant worlds. Experts predict that within the next decade, we might have a catalogue of dozens of worlds with confirmed or suspected biological activity. The search for life is also expanding to include planets around stars of different ages and compositions than those traditionally considered optimal for habitability. Very young star systems might reveal planets where life is just beginning to emerge, while very old systems might show planets where life has had billions of additional years to evolve and develop. Planets around metal-poor stars, which were once thought to be unlikely to host habitable worlds, are also becoming targets for investigation. Future missions to study potentially habitable exoplanets will likely include increasingly sophisticated approaches to searching for signs of complex life or even intelligence. While current techniques focus primarily on detecting basic biological processes through atmospheric chemistry, future observations might be sensitive enough to detect seasonal patterns that could indicate agricultural activity, atmospheric composition changes that might suggest technological civilization, or even direct detection of artificial structures on planetary surfaces. The development of interstellar probe missions represents the ultimate future goal in the search for life beyond Earth. While such missions remain decades or centuries in the future, with current technology. The discovery of K218b and potentially similar worlds provides concrete targets that justify the enormous technological development efforts required for interstellar travel. Breakthrough Starshot and similar initiatives are developing technologies that might eventually allow tiny robotic probes to reach nearby potentially habitable worlds within decades rather than millennia. The search for life within our own solar system continues to complement the search for exoplanetary life, with missions to Mars, Europa, Enceladus, and Titan providing additional opportunities to understand how life might arise and persist in different environments. The techniques developed for detecting life in our solar system often inform methods for studying exoplanets, while discoveries about exoplanetary atmospheres help guide the search for life closer to home. Statistical studies of exoplanet populations suggest that the discovery of K218b might be just the beginning of finding numerous worlds with signs of biological activity. Recent analyses indicate that potentially habitable worlds might be much more common than previously thought, with some estimates suggesting that billions of Earth-sized planets in habitable zones exist within our galaxy. If even a small fraction of these worlds harbor detectable life, the coming decades could see the discovery of dozens or hundreds of worlds with confirmed biological activity. The future search for life is also likely to reveal the incredible diversity of potential biospheres throughout the universe. While K218b appears to host life forms that produce atmospheric signatures similar to those created by terrestrial organisms, future discoveries might reveal alien biochemistries that create entirely different atmospheric compositions. Understanding this potential diversity of life will require developing new theoretical frameworks and observational techniques specifically designed to detect non-terrestrial forms of biological activity. Educational and outreach efforts in astrobiology are expanding rapidly to keep pace with the accelerating rate of discovery in the field. The concrete example of K218b makes the search for extraterrestrial life more tangible and accessible to students and the general public, inspiring new generations of scientists to pursue careers in astrobiology and related fields. Universities around the world are developing new degree programs in astrobiology, ensuring that future researchers will have the interdisciplinary training necessary to tackle the complex questions surrounding life in the universe. The future search for life will also increasingly involve consideration of the potential for contact or communication with extraterrestrial civilizations. While K218b shows clear signs of biological activity, the atmospheric signatures cannot determine whether intelligent life exists on the planet. As our observational capabilities improve, we might eventually be able to detect more subtle signs that could indicate the presence of intelligence or technology on distant worlds. The role of citizen scientists in the search for life beyond Earth continues to expand as more data becomes publicly available and analysis techniques become more accessible. Projects like Planet Hunters allow volunteers to help identify potentially habitable exoplanets in telescope data, while other initiatives enable citizen scientists to contribute to the analysis of atmospheric spectra from potentially life-bearing worlds. This democratization of the search for life ensures that diverse perspectives and approaches contribute to our understanding of life in the universe. We now know it is possible. The universe is far from empty, and we are only just beginning our journey to discover what lies beyond. The discovery of K218b has opened a new chapter in human understanding of our place in the cosmos, transforming the search for life from a hopeful quest into a systematic scientific investigation with proven methods and clear objectives. As our capabilities continue to advance and our understanding deepens, the future promises discoveries that will further revolutionize our conception of life, intelligence, and our cosmic significance in ways we can barely imagine today. In the vastness of space, we have found a world that could be home to life, and with it, the possibility that we are not alone. The discovery of K218b represents more than just a scientific milestone. It marks a profound turning point in human history, the moment when our species first found concrete evidence that life exists beyond our own blue marble, thriving on a distant world under an alien sun. As we reflect on this extraordinary journey of discovery, we are reminded of how far we have come in our understanding of the cosmos and our place within it. Just a few generations ago, we did not know if planets existed around other stars. the very concept of exoplanets was purely theoretical, confined to the realm of science fiction and philosophical speculation. Today, we not only know that such worlds exist by the thousands, but we have found one that appears to be teeming with life, a world that might be even better suited for biological processes than our own Earth. The story of K218b is ultimately a story about human curiosity, ingenuity, and our relentless drive to explore the unknown. From the ancient astronomers who first mapped the movements of the planets to the modern scientists who developed the sophisticated instruments capable of analyzing the atmospheres of distant worlds, this discovery represents the culmination of millennia of human scientific endeavor. The James Webb Space Telescope, with its revolutionary capabilities and unprecedented sensitivity, stands as perhaps the greatest triumph of human engineering and international cooperation, enabling us to peer into alien skies with clarity that would have seemed magical to previous generations. The atmospheric signatures detected on K218b tell a story of a world where life has not just emerged, but has fundamentally shaped the planetary environment in ways that create perfect conditions for continued biological prosperity. The oxygen that fills its skies, the methane that indicates active biological processes, the water vapor that suggests vast oceans, and the perfectly balanced greenhouse gases that maintain optimal temperatures all point to a biosphere that has achieved remarkable stability and harmony. What makes this discovery even more remarkable is the realization that K218b represents just the beginning of what we might find as our capabilities continue to advance. If we can discover a world with such clear signs of life, just 22 light-years from Earth, it suggests that life-bearing planets might be surprisingly common throughout our galaxy. The universe that once seemed cold and empty now appears to be filled with possibilities, with countless worlds where the chemistry of life might be writing its own unique stories across the cosmos. The implications of this discovery extend far beyond the purely scientific. The confirmation that we are not alone in the universe touches the deepest aspects of human consciousness and philosophy, challenging us to reconsider our place in the cosmic order and our responsibilities as members of a potentially vast community of life. The knowledge that alien biospheres exist and thrive changes how we think about environmental stewardship on our own planet, about the preciousness and fragility of life, and about our potential future as an interstellar species. The young minds of today will grow up in a universe where extraterrestrial life is not a matter of speculation, but a confirmed reality. Children learning about the solar system will also learn about K218b and perhaps dozens of other life-bearing worlds that we will discover in the coming years. This generation will likely witness the first detailed images of alien ecosystems, the first chemical analyses of extraterrestrial biochemistry, and possibly even the first communications with intelligent civilizations on distant worlds. The technological achievements that made the discovery of K218b possible represent just the first steps in what promises to be an extraordinary era of exploration and discovery. The next generation of telescopes will be even more powerful and sensitive, capable of studying the atmospheres of potentially habitable worlds in unprecedented detail. Future instruments might even be able to directly image the surfaces of nearby exoplanets, potentially revealing the seasonal changes of alien vegetation or the glint of sunlight off extraterrestrial oceans. The search for life beyond Earth has transformed from a lonely quest into a thriving scientific discipline with concrete goals and proven methods. The techniques that revealed the remarkable properties of K218b are being refined and improved, preparing us to study dozens or hundreds of potentially life-bearing worlds in the decades ahead. Each new discovery will add to our understanding of how life emerges, evolves, and shapes planetary environments throughout the universe. Perhaps most inspiring of all is the realization that the optimal conditions found on K218b might represent a glimpse of what Earth could become. The apparently superior environmental stability of this distant world suggests that planets can achieve even better conditions for life than those we experience on our home planet. Understanding how K218b maintains its perfect atmospheric balance and stable climate might provide insights that help us better care for our own planetary environment. The international cooperation that made the James Webb Space Telescope possible demonstrates humanity's capacity to work together in pursuit of knowledge and understanding that benefits all people. The discovery of life on K218b belongs not to any single nation or organization, but to all of humanity. It represents a shared achievement that transcends political boundaries and cultural differences, uniting us in our common heritage as children of the cosmos. As we look toward the future, the possibilities seem limitless. Robotic missions to nearby potentially habitable worlds might launch within decades, carrying sophisticated instruments designed to search for signs of life in alien soils and atmospheres. Advances in propulsion technology might eventually make crewed missions to worlds like K218b feasible, allowing human explorers to walk on alien shores and study extraterrestrial life forms directly. The discovery of K218b also opens up entirely new questions that will drive scientific research for generations to come. What forms does life take on this distant world? How similar is alien biochemistry to terrestrial life? And what can the differences teach us about the fundamental principles that govern living systems? Are there intelligent organisms on K218b? And if so, how might their understanding of the universe differ from our own? These questions remind us that every answer we find in our exploration of the cosmos leads to new mysteries and deeper wonders. The confirmation of life on K218b is not the end of our journey of discovery, but rather the beginning of a new chapter in which we explore not just the physical universe, but the biological universe, the realm of living worlds and alien biospheres that we now know exists beyond our own solar system. The story of K218b also serves as a reminder of the preciousness and rarity of the conditions that make life possible. While this distant world appears to be thriving with biological activity, the fact that we had to search 22 light-years to find such clear evidence of life suggests that truly optimal conditions for life might be relatively uncommon in the universe. This realization makes our own Earth even more precious and reinforces our responsibility to protect and preserve the remarkable biosphere that we call home. As we continue our journey through the stars, we carry with us the knowledge that life finds a way to emerge and flourish wherever conditions permit. The universe revealed by the discovery of K218b is not a cold and lifeless void, but a cosmos rich with possibilities, where the chemistry of life might be playing out on countless worlds beneath alien skies. We are part of something far grander than we ever imagined, participants in a cosmic story of life, intelligence, and wonder that spans the galaxies. The detection of life on K218b represents humanity's first definitive step beyond our cosmic isolation, our first concrete evidence that we share the universe with other living worlds. As we stand on the threshold of this new era of discovery, we can only imagine what other wonders await us among the stars. The universe has revealed one of its greatest secrets to us, showing us that life exists beyond our solar system in conditions that surpass even our own world. In the vastness of space, we have found a world that could be home to life, and with it, the possibility that we are not alone. As we continue our journey through the stars, may we never stop asking, what else is out there? The answer, we now know, is likely to be more wonderful and surprising than we ever dared to dream.